Okay, welcome back to the afternoon session. The next speaker is Dumke from Nanyang Technological University.
Okay, thank you. Thanks for inviting me here to this amazing workshop. Maybe a little bit oddball here. I will be focusing more, or so my background is atomic physics, but I'm doing also a little bit on the superconducting side. Maybe let me just sort of show from where I'm coming. I'm coming from Singapore. It's roughly down there. It's on the other side. And this is actually how it actually looks like. Temperatures are typically 28 degrees to, let's say, 30 degrees. Working in the Center for Quantum Technology. It's a national center in Singapore. Let's say, areas which are, let's say, researched in there are quantum communication and security, quantum processor computation and simulation, and also quantum sensing and metrology. There are, of course, some horizontals as well. That's advanced instruments developments, and of course, basic science. Actually, in fact, basic science is fairly big in there as well. To the center itself, we have about 226 staff, 230 staff. In there, we have 23 principal investigators, so people with their own groups. Currently, about, let's say, 100 PhD students. And also, since it's Singapore, we need to generate revenue. We also have, let's say, 6 startups spun out from the center. The center, as I mentioned before, is a national center. So it's actually distributed over the universities in Singapore. There are, let's say, 2 big universities, the Nanyang Technology University and the National University of Singapore. And let's say, my labs are mostly at the Nanyang Technology University, but also I have some operations at NUS. Okay. So maybe let's also emphasize a little bit. If you look now at, let's say, certain, let's say, key platforms which are out there, which, let's say, where actually quantum technology has progressed in the past. This is actually a personal pick, of course. And actually, there are, of course, neutral atoms, which are, let's say, neutral atoms ions, which are sort of, one could think of the best quantum systems which are available. There's each system is exactly the same as each other, so they're indistinguishable. And photons, and then on the other side, the main systems, which are superconducting circuits. It's fairly easy to, let's say, combine the systems to let them interact with each other. So there have been, let's say, over the last, let's say, 3 decades, quite a few experiments showing how to, let's say, interact ions with neutral atoms, for example, neutral atoms with photons, and photons with ions. So this is very well established in the community. What is not so well established is actually interaction of neutral atoms when superconducting qubits. There was recently a paper, of course, from here, from Schuster and Simon, which has shown some very interesting results, how you can actually achieve this, going, let's say, to millimeter waves. But let's say we also have looked into this a little more detail. Since it's actually, this workshop is heavily on the superconducting side and fabrication side, let me actually try to gear it a little bit to why actually atoms also have a relevance, right? So let's say hit some of the great things we can actually do with hydrocoated atoms or with atoms in general. For example, atomic quantum system. So this is, let's say, a typical atom which is used in the community for most or for quite a few experiments, Ruby 87. Actually, that's more or less one of the atoms where this whole business has started. There's, let's say, a lot of different frequencies in there, from, let's say, megahertz, gigahertz, optical frequencies, any type of frequency you can actually think of if you're going even to the Rydberg states. The nice thing is we can actually control, let's say, the external degrees of freedoms of these atoms fairly well. In fact, actually, we can remove the kinetic energy and cool down the system to, let's say, very low temperatures. So if you look actually at the de Broglie wavelength of this type of system, we can actually remove the energy, and with this, the kinetic energy, and with this, increase the de Broglie wavelength until it's overlapping, and then we can actually generate giant matter waves, Bose-Einstein condensate. This is actually, let's say, a picture from our lab where we have, let's say, a very simple Ruby 87 BC with 10 to the 5 atoms at a temperature of about 70 nanokelvin. Okay, so what can we do with this? Here is sort of one of, one could say, almost a textbook type of example. So we trap the atoms in a square, as you can see here, confine it in 2D. Then actually, splits the square into 2 slits, right? And then what we're doing is we just switch off the trapping potential and let the cloud expand in a 2D plane. And what we actually see is quite interesting. Well, as expected, we see here this very nice interference pattern. This is real matter wave interference. You see constructive and destructive interference of matter wave. Right? So it's a real macroscopic wave function we have in there. With, of course, quantum mechanical properties. Our funders say, okay, great, right? So you can produce nice pictures. What else can you do? We can actually use the system for building interferometers, of course. So if you have a matter wave, then that's, of course, what you want to do is you want to build an interferometer. And let's say we have in my lab, we have actually set up this portable interferometer here. It's measuring acceleration, gravity. The idea is the following. So here in this graph, you see this direction, the Z direction, let's say in the direction of gravity, and the X direction is time. So initially, we have our atoms here. We launch them up from here up in a fountain and apply a beam splitter pulse. So this is laser pulse, where we have, let's say, part of the wave packet getting a momentum from the photons and part not. So it's in a superposition state of having a momentum and having not a momentum. Then when the atoms are at the apex, we apply another beam splitter pulse, a mirror pulse, bi-pulse, and where we actually reverse the momentum distribution. So we take away the momentum from here and impart another momentum in this state. And then at the end of this interferometer sequence, we make another pi over 2 pis and project them back to their states. So and then we can actually measure here again this interference. And of course, the phase of the interference signal depends on the area, or let's say the sensitivity of the system with the phase shift in the interference signal depends on the area of this interferometer. And the, let's say, arm length in this case depends also on the acceleration, which is changing. So the relative arm length is changing if the acceleration is changing. With this, we can measure interferometrically precise the acceleration in Z direction with this gravity. As said before, so this is, let's say, the system here. We actually build everything by ourselves. So the electronics, the lasers, the vibration isolation. because we actually have to make sure that they are useful or usable in, let's say, harsher environments than a lab environment. So the lasers are double temperature stabilized. The optical systems are made in a very stable boxes with very small path lengths. And there's also a active vibration isolation of the last mirror, which is the most crucial part in the interferometer setup. However, the user will just see a black box. And the system is fully remotely controllable via the cloud, so that the students can sit at Starbucks and do the measurements. So this actually is, let's say, a typical signal. So this is, let's say, over, let's say, a few days, the gravity, and you're seeing very nicely this oscillation here, which is coming from the tides, the movement of the moon around the Earth. So that's, let's say, something which, yeah, is sort of the largest signal which we are measuring there. What I think also very important is for quantum sensors. Quantum sensors are not necessarily very precise compared to, let's say, classical sensors. Sometimes they can be more precise than classical sensors, but classical sensors can always keep up with, or let's say, a lot of occasions keep up with quantum sensors. In my opinion, the, let's say, most important feature of these quantum sensors is that they are accurate. Accurate means that I am doing measurement today, I will exactly have the same measurement tomorrow again. Right? So one way of thinking this, especially, let's say, for this gravimeter. So a classical gravimeter works that you have a mass and a spring. If I do a measurement now with the gravity, and let's say sometimes later, then what actually is, can actually happen is that the K constant of the spring is changing, because I'm comparing my measurement to a, let's say, large, massive artifact, a classical artifact. And this artifact can actually change. The spring constants are changing, springs are aging in time. So we see always drifts if you're using classical sensors. In this sensor, we're actually comparing, at the end of the day, our measurement to the speed of light, which is not changing. And of course, fundamental constants, which gives the structure of the atom. And this is actually very nicely seen in this diagram here, where we have, again, the, let's say, acceleration in microguy. Microguy is about 10 to minus 9 G. G is the gravitational acceleration versus time. So this is the N deviation. We see here very nicely that it's sort of going down always. So a classical system would actually go up for larger, let's say, longer times. And we can actually average it down for much, much longer, if necessary. Okay. This system we have actually used also outside because, let's say, again, our funder says we have to do something for the community, and did a survey, or let's say a few surveys in Singapore. So for example, we could actually place the system here in this container close to actually a drilling site where Singapore is very interested in geothermal energy, and we would like to see actually the underground structure of there and try to actually map it and see if the area is actually, let's say, useful for extracting geothermal energy. So this we had, let's say, also a reference station, and we did then our survey. What's actually also important is for this survey, which makes it also very difficult, is that you have to actually measure also the height of the sensor with extreme precision. Always, so within, let's say, a few millimeters. So 1 centimeter change in height is about 3 microguy change in acceleration. And what we actually have seen there in this survey, for example, is here a predicted fault line where we see actually the change in the gravity signal. We have done, let's say, other surveys on, let's say, islands also in Singapore. This I can't share here. And done there also, let's say, gravity surveys at the close to hot springs. So let's say this sensor is, it's really, let's say, fun sensors which you can use in the field, right? Done with atoms. They are fairly large, as you still can see, right? So what we can actually do to shrink them down a little bit further. So there's actually this idea of atomtronics, where we can, in principle, write, let's say, circuits with light fields, so you can trap and guide either-code atoms. Similar, let's say, to what you actually know in, let's say, your superconducting circuits, where you just write them on a substrate. Here we can write them in free space. So, for example, circuits could be like this type of, let's say, split type of systems, where you have here lattice of atoms with a few defects. And you can, let's say, generate this type of energy structure, and even, let's say, thinking of realizing, let's say, a qubit in this system. However, of course, it's not really useful because the time scales are in the range of seconds. Or you can even, let's say, realize, let's say, metawave resonators, or other things, anything which you can imagine. Okay, so this is, I've hopefully emphasized a little bit why, let's say, atomic systems are extremely interesting, and why, yeah, it would be nice actually to let them interact also with superconducting systems. Maybe quickly also for the superconducting systems, it's in our lab, we are also setting up, let's say, a processor platform, where we have, let's say, a few small quantum processors, which can be used by the community within Singapore. They can run their small little programs on them. So we have, let's say, some processors from IQM, 20 qubit and 5 qubit system. We have our own in-house developed systems still under work in progress with 8 qubits. And the system can actually be scaled up to, let's say, 50 qubits or even larger. For this, let's say the advantage of this system is, of course, that, let's say, the user has, let's say, full control, price level control of the, let's say, processor. And also that we actually have, let's say, access by ourselves, made actually this, let's say, control system, so that, let's say, scaling up it to, let's say, larger, let's say, qubits won't become, let's say, too expensive in future. This is based on a RF-SOC system from Xilinx, and has, let's say, a very high number of channels. Right. Okay, so now let's say I've emphasized a little bit on the superconducting side and on the Nuja atom side. Let's maybe think about how we can actually connect these two things. Okay, so there's a very old idea from, let's say, Shirkov and Solar, Dumke as well, where one could think of, okay, we can actually in principle bring the atoms or molecules close to a strip-line cavity and have, let's say, inside there also a, in this case was a Cooper box. However, if we actually, let's say, look at the, let's say, interaction strengths of these types of systems, it's fairly weak and typically in the range of about 10 kilohertz. But sort of this was the beginning of the idea of, let's say, how we can actually try to let these two systems interact with each other. A few years later, there was even the idea of using a set of, let's say, thermal atoms or thermal cloud, a coherent cloud. So in this case, let's say, Bose-Einstein condensate, to bring it, let's say, also again close in this case to a squid type of system. It was the idea from Fisher that we can actually exploit the, let's say, meta wave properties or let's say the microscopic wave function properties of, let's say, this atomic system, and get, let's say, a square root n enhancement in the coupling, which will, let's say, about 10 to the 6 atoms in a VEC, which is a reasonably high number, would actually lead to about roughly 10 megahertz coupling. What we actually were thinking of is to directly couple the atoms to a superconducting qubit. In this case, we looked at charge qubits, where we actually bring the atoms more or less in between the capacitor of the qubit. Or in reality, it will be, let's say, if you have, let's say here, it's one of our transform qubits, we bring them very close in between this two capacitor plates. So they are interacting with the French fields. If we do so, and then let's say we excite the atom in the Rydberg state, and with this we can actually achieve some interaction. Sort of a hand-waving picture would be that, let's say, the atom in the ground state is not doing anything. So the superconductor, or let's say the qubit, does not see it. If you go to the highly, let's say, excited Rydberg state, the dielectric constant of the medium inside is changing. And with this, actually, also, we have an interaction to the qubit. And on paper, at least, we could show that there is, that we can make state transfer from the atom to the qubit and from the qubit to the atom back with, let's say, fidelities in the range of, let's say, 95% or so. However, for this, we have to be very close or fairly close to the surface in the range of, let's say, 10, 20, 50 micrometers. The problem is that if you bring atoms close to a metallic surface, the atom will start to see, let's say, thermal fluctuations on the surface. Okay, and let's say from the fluctuation dissipation theorem, this leads actually to a fluctuation in the electromagnetic fields, and which can be actually picked up by the atoms. So the atoms can actually have, let's say, if they are trapped in a magnetic field, have a spin flip, which then at the end of the day will lead to the fact that they're leaving the magnetic field. And this is actually a, let's say, a measurement where actually the lifetime of the atoms is plot versus the distance from the chip surface, and you actually see that lifetime actually drops significantly the closer you go to the chip surface due to this effect. However, if you're actually going from, let's say, normal metal to a superconductor, this is actually lifted. So here, what we have shown is that instead of using, let's say, gold surface, if you're using niobium superconductor, we could actually, let's say, increase the lifetime at, let's say, distances or reasonable distances of, let's say, 10 micrometers by orders of magnitude in theory. Right. So, and if you also put, let's say, just a very thin 50 nanometer gold film on top of it, you still have, let's say, this high enhancement. Okay, so meaning actually, in principle, this idea of, let's say, going close to a superconducting chip is not totally ridiculous. This is, let's say, the typical experiment where we're trying to do this. So here we have our system with a magnetic optical trap, a Siemens lower. Actually, that's a little bit old, this picture. Now we have a 2D mode there. And there we have a dilution refrigerator in between a transport system. Maybe let me elaborate a little bit more on this transport system here. So here's, let's say, our magnetic optical trap. Then we have a tube, vacuum tube, which connects this system to a dilution refrigerator. And to actually transport the atoms, what we actually have are multiple quadrupole magnetic coils, where we do a transport horizontal and vertical into the dilution refrigerator, bridging actually a temperature of about between 300 Kelvin and 14 to 17 millikelvin. Now, this is a simulation of the, let's say, magnetic field. We can actually move the atoms in the minimum of the magnetic field into the dilution refrigerator. In the dilution refrigerator itself, we have here a small 4-wire guide, which and let's say another quick coil, or where we can actually, in principle, cool down the atoms even further. So maybe just as a sort of side remark, the atoms which we are transporting into the fridge are fairly hot. They are around about, let's say, 50 to 100 microkelvin. The reason for this is because the transport takes some time and they are in a quadrupole field. So if you would decrease the temperature, then you would have Majorana spin flip losses. So if we go to, let's say, maybe microkelvin or so. So that's the reason why we need, let's say, this higher temperatures. And in principle, we can actually decrease the temperature further up here with, let's say, evaporative cooling. Then inside here, we have, let's say, as mentioned before, this wire guide, where we can actually trap the atoms and then move them, because it's a little bit slanted, into a 3D cavity, which is shown here. Okay. This is, let's say, showing the transport sequence in the, let's say, various stages, the horizontal stage and the vertical stage. We start around with, let's say, 10 to the 9 atoms, 2 times 10 to the 9 atoms, and at the millikelvin stage, with about 5 times 10 to the 8 atoms. Yeah. Typical, let's say, trap lifetimes, because we are, let's say, this very low temperatures of about a few tens of millikelvin, 70 millikelvin, for example. We see actually lifetimes up to about 800 seconds, which are about 13 minutes. At this point in time, this was the record in terms of, let's say, trapping atoms in vacuum chambers. But nowadays, let's say, with glass cell and very good pumps, you can also achieve this at room temperature. Please.
I might be mistaken, but was it in your work that at some point you saw that the pressure would go up eventually from saturation of surfaces? Do you see that effect?
So we see some effect from saturation of the surfaces, which is an electric field.
Oh, I see. But there's no like a pressure dropping, like lifetime of atoms going down eventually because
no.
surfaces get saturated.
No, that's not this. I mean, the cold surface is very, very large, so it's a full.
So the pressure, you don't have to warm up or anything. The pressure is just
Yes, exactly. Yes, correct. So yeah, so I think if you are, let's say, very low temperature, 70 millikelvin, everything will just freeze. In fact, actually, most likely we are limited here in the lifetime, depending actually on the, let's say, residual noise we have in the magnetic field. So we have actually seen if we, let's say, filter the magnetic field, or let's say the current more and more, we see, let's say, see an increase in the lifetime. But most likely there's still noise there which limits it. Pressure should be as good as you can imagine. So inside the cavity, we have, let's say, a transform qubit, where we actually bring the atom, let's say, close to this transform qubit. Of course, one has to make sure that, let's say, this guide goes into the cavity there where no current is flowing, to actually not decrease the Q factor. However, this cavity is just being used for reading out the qubit. And we are actually measuring, or let's say the idea is to measure the interaction between, let's say, the qubit and the atomic cloud. This is just a simulation. Unfortunately, we don't have a measurement yet due to some technical reasons. The fridge broke down, and this cost out a few years. Anyways, and what let's say we see, let's say in the calculation is that in principle, let's say with the experimental parameters which we have, we should see, let's say, a distance of about, let's say, 50 micrometers roughly, still a coupling strength of about 20 megahertz. So it's not too bad. So you should see some, let's say, shift in the frequency of the qubit, measurable shift of the frequency of the qubit. Come back to this question. What we also did, of course, is since we are, let's say, bringing atoms always up in there, right? We are making the system a little more dirty. And what we are seeing is that, let's say in this picture, you see, let's say we have here an atomic cloud, and we do a spectroscopy, a Rydberg spectroscopy, and looking actually at the shift of the Rydberg state, right? And you can actually see here, there where you start to see the atoms, at this frequency means that the Rydberg state is shifted at this particular frequencies. You see, let's say, very nicely, here the 5-half state, the 3-half state, the 1-half state, which sort of bends over here, following this Stark map. Interestingly is that this electric field is actually depending on temperature. It's changing with temperature. The reason is that we are going from, let's say, a chemisorption, which you have typically at room temperature. So the atoms will just stick on the surface and have ionic bond. So the part of the charge goes into the surface and they form a dipole, and with this electric field. 2, if you decrease the temperature, you will start to see also physiosorption. So the atoms will hover in the van der Waals potential, and then they, let's say, see their image charge, or they can see their image charge and start to polarize, which gives you, funny enough, electric field in the opposite direction, which can be very, or which can be in principle a problem for the Rydberg states if you actually want to bring them closer and look at coherent interaction. However, there was an experiment from Haros group, which actually have shown that if you saturate really your surface with rubidium atoms, so have a, let's say, thin layer of rubidium on all your surface, you see actually that let's say the coherence of your Rydberg states is actually, if you're doing Ramsey spectroscopy, is actually increasing, or it's decently high, up to, let's say, a few hundred microseconds. So meaning also this, let's say, effect that, let's say, maybe you have some residual atoms on your surface which generate electric fields can be circumvented or enhanced, and then you don't care about it anymore. That's all I want to share for today. I hope I've shown you that, let's say, for quantum technologies, atoms play a role. And there's, let's say, certain interesting things we can actually do with atoms. Even use them for sensors. It would be great to actually use, let's say, the best of the two worlds, the best of atoms. So let's say the high, long coherence times, maybe use it in memory, the very rich electronic structure of atoms. So you can actually make any type of frequencies you actually want. With the, let's say, try to merge this with the scalability of superconducting systems. And yeah, so try to bring them together in a cryogenic environment. Okay, thank you, and happy to answer any questions.
Sorry, so for the electric fields, is the issue that the electric fields are changing in time because you have some duty cycle of your experiment, so like the charges of dipoles are kind of changing in time? Or is it just that having any even static, because in principle you could use electrodes and like cancel like a static field. But is it
Right,
the
so
dynamic?
you have a field gradient.
I see. Oh, okay, okay.
So you have to make sure that you will always at the same point with your atoms, and let's say the extension of the atoms should not be large compared to the gradient. Also, since actually, let's say very low temperatures, you have patches here. Maybe it won't be, let's say, the same from cool down to cool down. Or if you start to bring, let's say, more and more atoms there, you not necessarily know where you're losing them, and they form from different patches.
But you don't see the changes in time, like during your experiments.
Let's say we see changes in times when we're cooling it down.
Okay.
Right. So at the beginning part, when you talk about atomic interferometry, you said you compare the result with speed of light. Can you elaborate on what that means?
Okay, yes. Yeah, exactly. It's not very intuitive. Okay, so in principle, let's see how this thing is working, right? There, let's say, different views on this, or let's say different picture. So I think the easiest picture is we have here, let's say, so what is here is a mirror and a laser beam from top, right? So we have a laser beam from top, mirror, which forms a standing wave, okay? And at the end of the day, we compare the wave function of the atom with the wave function of the standing wave. So we see at which fringe it is, right? So, and this actually, at the end of the day, let's say, or let's say, the comparison of the phase of the atom of the atomic matter wave with the phase of the light field gives us the interference, right? So, let's say you're comparing the, let's say, frequency of the light, which we know, right, which is also given by the speed of light at the end of the day, which gives us the phase of the standing wave with the phase of the atom. So that's actually how, at the end of the day, it's comparing the speed of light, making measurement, let's say, in comparison to the speed of light. Right. Okay.